Hello, and welcome to our introductory video on homogeneous Sturm-Liouville boundary value problems. These are boundary value problems of the following form. The differential equation part reads, first derivative on the product p of x times f prime plus q of x times f equals lambda times r of x times f over the interval a to b, where p, q, and r are given functions, lambda is a parameter, and f is the unknown that we want to find, coupled with the two boundary conditions, alpha 0 times f of a plus alpha 1 times f prime of a equals 0 for given constants alpha 0 and alpha 1, and beta 0 times f of b plus beta 1 times f prime of b equals 0 for another set of given constants, beta 0 and beta 1. And here are some details on all the things that are given to us in the problem. P is a continuously differentiable function on a to b. Q and r are continuous functions on a to b. P and r are both positive valued functions. Q is real valued. So in particular, all three of our functions, p, q, and r, are real valued. And lambda is a fixed real number. The numbers alpha 0 and alpha 1 are not both 0. And the numbers beta 0 and beta 1 are likewise not both 0. So at least one of alpha 0 and alpha 1 is non-zero, and at least one of beta 0 and beta 1 is non-zero. Now why? Why should we study a problem that looks like this? After all, the differential equation part looks very, very specific. And the boundary conditions, too, may seem a little contrived or forced. What's the value in a problem like this? First of all, it arises quite naturally in applications. In the lecture notes, we see a very natural way that separation of variables for a more general heat equation type PDE yields this kind of boundary value problems for one of the factors. Two, although the ODE part looks strange, and it should, it turns out that you can write any ODE of the form phi of x times f double prime plus psi of x times f prime plus theta of x times f equals 0 in the Sturm-Liouville form of the left-hand side of the ODE above if your coefficients phi, psi, and theta are reasonably nice. In other words, this differential equation on the left-hand side of the boundary value problem, although it's strange, it turns out to be equivalent to a lot of more general differential equations. So why work with this stranger, more particular form? Well, there is a lot of rich mathematical structure for a boundary value problem when you've written it in this particular form. So you can get a lot of mileage out of this strange-looking differential equation, so it is in fact worthwhile to study. Here is the challenge of this kind of problem. Solving the differential equation is, at least in theory, not that hard. Here's why. In your differential equation, p, q, and r are all continuous functions, and yes, you'd have a p of x times the highest derivative f double prime, but that p is positive, so you could divide by it. The differential equation here always has solutions. That's not what is interesting in this problem. Rather, it's trying to find a solution that also satisfies the boundary conditions, that is trickier, and that has a lot of a richer mathematical structure than just solving the ODE part. We will do in detail one example to start with that shows how we grind through solutions to a boundary value problem, and also what are some properties of these solutions. Namely, we want to look for two things. We want to look for the solution f, and also the values lambda of that parameter for which it works. Let's do something concrete. Example 2.7.3 asks us to find all real numbers lambda and all non-trivial functions f, such that f double prime plus f equals lambda f on the interval 0 to pi, and f of 0 equals f of pi equals 0. By non-trivial, I mean not identically zero functions, that is, functions that take a value other than 0 for at least one point. So although I've written this problem in a slightly different form from the previous slide, it is indeed a Sturm-Liouville boundary value problem. Here's why. If you look at the boundary conditions f of 0 equals f of pi equals 0, well, that's the same thing as the two sets of conditions 1 times f of 0 plus 0 times f prime of 0 equals 0, and 1 times f of pi plus 0 times f prime of pi equals 0. So now in each set of the boundary conditions, the ones at 0 and the ones at pi, you have at least one coefficient non-zero, namely the coefficient on f of 0 and f of pi. So this does meet with the definition that we had before. Now the ODE part here, f double prime plus f equals lambda f, we can rearrange that to a constant coefficient homogeneous ODE. We know how to solve that. It all depends on what lambda is. And lambda in this problem will be a real number, so I can order lambda as negative, 0, or positive. And yes, that's what we'll do. We'll look at lambda less than 0, lambda equals 0, or lambda greater than 0, and we'll develop some different behaviors in each case. If this feels familiar, this is very much what we did in certain separation of variables problems for the heat equation and possibly other equations where we had an arbitrary real parameter and we needed to consider cases on it. In particular, when we look at lambda less than 0, we'll write lambda equals minus alpha squared for some number alpha that's positive. And we'll also write a positive lambda as lambda equals alpha squared for some alpha positive. This is a very popular trick to rewrite the parameter in this sort of negative squared or positive squared way, and we'll do it each time. So case 1. Lambda equals minus alpha squared, which will be negative, and here alpha is a positive number. What is the ODE? F double prime plus f equals minus alpha squared f. That rearranges to f double prime plus alpha squared plus 1f equals 0. As promised, constant coefficient, second order linear homogeneous ODE. We know how to solve it. Namely, alpha squared plus 1 is positive. Let's abbreviate mu equals square root of alpha squared plus 1. And then the solution has to be f of x equals c1 times cosine of mu times x plus c2 times sine of mu times x. That solves the ODE. What about the boundary conditions? We need 0 to be equal to f of 0. What is f of 0? That's just c1. And we need 0 to be equal to f of pi. And what is f of pi? That is just c2 times sine of mu pi, since we'll now assume that c1 is 0. So if we take c2 to be 0, then f would be identically 0. It would be trivial. It's not what we're told we're interested in. Instead, we want this factor sine of mu pi to be equal to 0, so that means we want mu to be an integer. That is, we want the square root of alpha squared plus 1 to be equal to k for some integer k, but square root of alpha squared plus 1 is always going to be positive, so we really want k to be a natural number, not just any integer. Let's rearrange this a little bit. We have square root of alpha squared plus 1 equals k, if and only if alpha is equal to what I'll call alpha k, which will be square root of k squared minus 1. Now, we want alpha to be a positive number, so I can't just take k to be any integer. I need k to be greater than or equal to 2, because if k were equal to 1, then alpha would be equal to 0. And so we see the only lambdas that are negative that produce a non-trivial solution are these numbers that we'll call lambda k equals minus alpha k squared, which will be 1 minus k squared for k greater than or equal to 2. And in that case, the solutions f have to be scalar multiples of fk of x, which will be sine of root alpha k squared plus 1 times x, which will just be sine of kx. So in the lambda negative case, we get a discrete set of decreasing values lambda k and functions or solutions that are always scalar multiples of sine of kx. These are the only possible non-trivial solutions when lambda is a negative number.